Hey guys, Mr. Backberg here. In this video, we're going to look at the derivative. As we're looking at any general function y equals f of x, the average rate of change of y with respect to x on the interval from a to b is delta y over delta x, which can be found by doing f of b minus f of a over b minus a. And geometrically, if we were to look at a graph, this is the slope of the secant line through the ordered pairs a, comma, f of a, and b, comma, f of b. Now, as we start to move away from the idea of average rate of change or average velocity to instantaneous rate of change, that's where we start to get the idea of a derivative. So the derivative of a function f at x equals a, which is denoted by f with this apostrophe of a, and we read that as f prime of a. So we would say that f prime of a is equal to the limit of f of x minus f of a over x minus a, as x is infinitely approaching that a value. And that's all provided that this limit exists. So geometrically, if we were looking at the graph, this is where we start to get the idea of that slope of a tangent line of our function f at the specific point a, comma, f of a. Now, this definition for a derivative may look a little bit different, but it is saying the same exact thing. This just makes some of the computations a little bit easier later on. So we've got the derivative of our function f at x equals a, again being denoted by f prime of a. So we've got f prime of a equals the limit of f of a plus h minus f of a all over h, and we're doing this as our h value is approaching 0. And again, this is provided that the limit exists. So we're going to look at an example where we find the derivative of a function at a specific point. So remember, what that means is we're finding the instantaneous rate of change of our function at that specific point. And I've got our second definition for that derivative written over here. That's the definition that we're going to use to help us out. So we're going to find f prime of 4 if our f of x function is 2x squared minus 3. So we're going to do this f prime of a with an a value of 4. So we're doing f prime of 4. So that's going to be the limit as h approaches 0. And on the top of our fraction, what we're supposed to do is f of a plus h. And remember, we're dealing with an a value of 4. So I'm just going to write these over here for right now. So f of 4 plus h in our function means that we're supposed to get rid of that x that's in there and replace it with this 4 plus h. So this first piece is going to say 2 times 4 plus h squared minus 3. But then we're supposed to subtract off f of 4, meaning that we're going to get rid of the x in our function and just replace it with a 4. So that's going to be 2 times 4 squared minus 3. And then this is all over h. So as we're doing this 4 plus h squared right here, we're going to have to FOIL that out. So we're taking 4 plus h times another 4 plus h. So 4 times 4 is 16. 4 times h is 4h. H times 4 is another 4h. And then h times h is h squared. So on top of my fraction, this is going to be 2 times 16 plus 8h plus h squared minus 3 minus, now on the back end here, there's no variables in here, so we should just be able to simplify this down. 4 squared is 16 times 2 is 32 minus 3 is 29. And this is all over h. Now I'm going to be able to combine that minus 3 and that minus 29 on the back end to get minus 32. If I distribute this 2 in, we're going to get 32 plus 16h plus 2h squared. And this is all still over h. Now that positive 32 and that negative 32 are going to cancel each other out. So we're going to get 16h plus 2h squared all over h. Now what I can actually do with this, if I look at the numerator, each one of these terms has an h in it. So I'm going to take out an h as a GCF. So it's going to give me h times 16 plus 2h, and this is all over h. Now this h on top and on bottom are going to cancel each other out. So then that's going to leave us with 16 plus 2h. Now I'm going to scroll all the way back up here because we're looking at this limit as h is approaching 0. So what that's going to allow me to do is some direct substitution and plug that 0 in for my h here. And 2 times 0 is 0, and if I add 16 to 0, then I get 16. So we were doing this derivative. We were looking at f prime of 4, and we got 16. So that means the instantaneous rate of change at an x value of 4 is 16. Now, there was a lot of algebra and a lot of simplifying that I went through as I solved to figure out what this derivative was. And honestly, that's probably the hardest part of calculus, is doing all of the algebra simplifying. The calculus itself isn't generally too taxing. It's all of the algebra that happens after you do the calculus, all of the simplifying that needs to happen after you do the calculus. That's where people typically run into issues, so you need to be very careful with your algebraic steps along the way. Now, we can just look at a derivative as a function of x. We don't need to have an a value that we're plugging in. So if we've got a function y equals f of x, the derivative of the function f with respect to x is the function f prime, whose value at x is f prime of x equals the limit of that f of x plus h minus f of x all over h, as h is infinitely approaching 0, for all values of x where our limit exists. So what's different here is, instead of plugging in a specific number for that x or for that a value, we're just going to be leaving that x value in our function. Now, as Leibniz was doing his version of calculus, he wanted to emphasize that the derivative was a slope. So instead of using this f prime of x notation, he used the notation dy over dx. It means the exact same thing as this f prime of x. So as you're moving through calculus, you may see this dy dx notation a lot. That just means that you're dealing with a derivative. So in this example, we're going to look at finding the derivative of the function f of x equals x squared. So I've got our derivative definition written over there to remind us what we're supposed to do. So if I want to find f prime of x, what I'm supposed to do is take the limit as h is approaching 0. Now this f of x plus h means in our function we're getting rid of the x and we're replacing it with x plus h. So this first part is going to say x plus h squared minus, I'm supposed to do my function f of x, but I know that my f of x function is just x squared, and then this is all over h. Now I'm going to need to square out that x plus h, so I'm taking x plus h times another x plus h, and we're foiling that. So x times x is x squared. X times h is xh. H times x is going to give me another xh. And then h times h is going to be h squared. If I combine these like terms in the middle, I'm going to get x squared plus 2xh plus h squared. So I'm going to fill that in on the top of my fraction. X squared plus 2xh plus h squared minus x squared all over h. Now I see this x squared in the front and this minus x squared on the end. Those are going to cancel each other out. So we get 2xh plus h squared, and this is all over h. Now what I can do on top, each one of my terms has at least one h in it, so I'm going to factor out a GCF. So we're going to have h times 2x plus h, and this is over h. This h on top and on bottom will cancel each other out, leaving us with 2x plus h. But again, we're looking at this limit as h is approaching 0. So I'm going to be able to plug in that 0 for my h right here, and 2x plus 0 just gives me 2x. So we can say that f prime of x is equal to 2x for the function f of x equals x squared. And again, you have to be very careful with your algebraic steps along the way. Like I said, it's not usually the calculus that gets people in trouble. It's all the algebra that follows. We're going to do one more example in here. We're going to find dy dx if y is equal to 1 over x. So remember, this means we're finding a derivative. So we're supposed to do the limit as h approaches 0 of f of x plus h minus f of x over h. So the first thing I'm supposed to do is f of x plus h. So in my function, I'm supposed to get rid of the x that's in there and replace that with x plus h. So that first piece is going to be 1 over x plus h minus, I need my function f of x, so that's just going to be the 1 over x, and this is all over h. Now with these fractions on top, we're going to need common denominators in order to put them together. So I'm going to multiply this first fraction by x on top and on bottom, and I'm going to multiply this second fraction by x plus h on top and on bottom. So what that's going to leave me with is x over x times x plus h minus x plus h over x times x plus h, and this is all still over h. Now when I combine these fractions, these x's are going to end up canceling each other out, and on the top of this fraction there's going to be a negative h over x times x plus h, and this is all over h. Now I'm going to rewrite how this is written. We don't typically like to deal with multiple fractions within the same problem, so I'm going to turn this into a multiplication problem. So I'm going to leave the fraction on top the same, so negative h over x times x plus h, but instead of dividing by h, I'm going to multiply by 1 over h. And then I can see some canceling happening in there because we've got this h showing up on top and on bottom. So I'm going to cancel out those h's, but be careful so you don't lose your negative. When you multiply these together, your numerator becomes negative 1 over x times x plus h. Now remember, we're doing a limit here as h is approaching 0. So if I fill in a 0 for that h value, then this set of parentheses just turns into an x. And on bottom, if I take x times x, we're going to get x squared. So we end up getting negative 1 over x squared as our dy dx. So that's our derivative for the equation y equals 1 over x. That's going to be it for this video. Thanks for watching.